Welcome everybody to this last session of the afternoon about deformed entropy, cross entropy, and relative entropy. We'll be sharing the first half, and my co-chair will do the rest. And our first speaker today is Olivier Rioul, who will talk to us about primer on alpha information theory with applications. Thank you. Please, Olivier.
Thank you very much. This is a talk entitled "A Primer on Alpha Information Theory." So I just want to attract the community's interest on a kind of more flexible theory, which focuses on random variables rather than on probability distributions. It's just a continuation of the classical Shannon theory. So I will be talking about entropy, and the alpha modification of entropy is well known. This is the Rényi entropy. I'll talk also about the conditional version of that, about the alpha divergence, which is thus the Rényi version of divergence, which you all know about, I guess, and also about mutual information. What is the appropriate generalization of mutual information in this case? And what also is the conditional mutual information, and so on and so forth. And so these quantities in the classical case alpha equals 1 proved very useful for solving coding problems or cryptographic problems and such. And the parameter alpha adds some more flexibility, but we still have this very important property that we need for solving those coding or cryptographic problems, and mainly some basic properties, uniform expansions, and so on. I will talk about this later in my talk. Also, the well-known fact that conditioning should decrease entropy, or that processing should decrease information and such, things like that. Okay, and so as a limiting cases, so alpha would be a positive parameter, either between 0 and 1 or between 1 and plus infinity. And in the limiting case, alpha tends to 0, then you will recover essentially log of volumes, log of measures, like in a Hartley paper. And when alpha tends to 1, you recover, of course, the classical Shannon's information theory. And when alpha tends to infinity, there will be an interesting connection with the estimation theory that I should talk about. All right, so first for some basic conventions. Every time I use probability distribution, I will assume that there is a dominating sigma finite measure. And then I can talk about densities. And this will cover the discrete case, like mu is a counting measure, and there's just a PMF, so the density is just a PMF, or the continuous case where mu is a Labec measure, but you can, and then you have the PDF, the usual PDF, but of course you can imagine more general situations. And whenever I consider several probability distributions, because of this property here, there will always be a possible dominating measure. And also, if I change the dominating measure, I would change the density accordingly. Sometimes it is important to have quantities which are independent of the choice of the dominating measure, and sometimes not. Okay. So for example, discrete case, you would have the probability as a sum. Continuous case, it's an integral. You can imagine other possibilities. Deterministic would be a Dirac. Uniform, you can define it in a general way, either discrete or continuous, and so on and so forth. Okay. So whenever we have several random variables together, then we can imagine that we have a product, which a dominating measure, which is given by a product, tensor product. And then you can define the conditional probability distribution, P of y knowing x, okay, which will have all the interesting properties. And in particular, there will be no measurability problems and so on and so forth. So that's what I define what Shannon called a channel, which I call here is simply a transformation. So it can be a random transformation with input x and output y, okay, given by this conditional distribution. Like, for example, if it's a deterministic function f, then you will have a Dirac. If the output is independent from the input, then simply P of y knowing x doesn't depend on x, and so on. Or the additive channel would be given by this, and so on. More generally, you can have Markov chains, that is successive transformations. satisfying the Markov property, which is given here. So for 3 variables, it's essentially given by this conditional independence condition, okay? And so there's no errors because you can see a Markov chain in both directions, because the actual Markov condition or the conditional independence is actually symmetrical in this case. And that's about it for the basic conventions, okay? So all of the integrals I shall be considering will be always integrals of measurable and non-negative functions, and Fibonacci theorem always applies and so on. Okay, so what are the specific notations that I shall use? Well, first of all, I define the alpha modification of a probability density function, which is sometimes called S-score distribution. And in denominator, you can see, well, something related to a norm. It's a norm when alpha is greater than 1, then you have Minkowski inequality, and it's convex. But when alpha is less than 1, you have the reverse Minkowski inequality, and then it's concave. Of course, this norm depends on the choice of the dominating measure. And more interestingly, let me define a kind of inner product, okay, which is given by the integral of p to the alpha q to the 1 minus alpha d mu to the power of 1 over alpha, okay? And now this is mu independent. I mean, this is independent of the choice of the dominating measure because it can be factorized as such. And you have Hölder inequality. So Hölder inequality would hold for alpha less than 1 in this case, and the reverse Hölder inequality for alpha greater than 1. And so essentially it's either less than 1, because this is actually evaluates to 1, okay? Integral of p is 1, integral of q is 1 for probability distribution p and q. Okay, so you either have less than 1 or greater than 1, and we shall, of course, use these properties later on. We have some other basic properties here. First of all, when one of the probability distribution is uniform, then we have this link between inner product, say, and norm, okay? Pu is m to the alpha minus 1 over alpha, norm of p alpha. And we have what I call the golden formula. That is, but if you have a joint distribution on both sides, and you can kind of decompose in this way. This is very trivial to check from the definitions. Just it's a matter of computation. And so this will be very important in the following, for the following properties. So alpha entropy is simply Rényi entropy of order alpha. This is well known. Of course, what you recover Shannon's entropy when alpha tends to 1. I will not say that again. I mean, every time alpha tends to 1, you recover the classical quantities. You have this uniform expression that is, if p is uniform, then it's simply log of m, so it's number of informational units, like a Hartley. And you have the binary expression, and of course it depends on the choice of the dominating measure, and that explains why, you know, in a discrete case and a continuous case, you have so many different properties. They're not the same. Okay. Of course, you have this other definitions called Fowler's entropy, which is related to h of alpha, but which I feel is not a good quantity here for my purpose, because it's not even constant for uniform distribution. I'm in constant in alpha. Anyway, conditional alpha entropy. So how do I define conditional alpha entropy? There are many possible definitions actually, and there has been many publications on many variations of this. But I feel that the best definition is the following: you consider the Rényi entropy, okay, the alpha entropy, for a given value of y, and then you have to average over y, okay? And everything depends on how you average. And here you average inside the logarithm, okay? And that gives you this definition here, okay? And you can make it like, okay, you can develop that. This is Arimoto's conditional entropy that Arimoto introduced in the 1970s, okay, for coding problems. And it turns out that it has all the interesting properties. So, of course, it's consistent in the sense that if y is constant, if it is 0, for example, then you recover the alpha entropy. This was not already, it's not the case for some other definition. It's still depending on mu, but you have the nice property. So using the convexity or the concavity of the alpha norm. You can simply, you can derive the relation h alpha of x given y z is not more than h alpha of x given z, okay? And in particular, when z is constant, that means that conditioning reduces alpha entropy. So that's nice, okay? It's knowledge reduces kind of uncertainty, if you like. Data processing, the famous data processing inequality is very important for solving coding problems, especially converse theorems. And here you have that property that the data processing increases entropy. Okay, whenever you have Markov chain x, y, z, then going from y to z is like making some processing, and that reduces the conditional entropy. All right. Some other definitions that have been proposed in the literature. There has been a whole article on this. So you could have average over y, directly this quantity, or you could have. Okay, so there's so many definitions, and neither of them satisfy all of these properties. So that's why I feel that Arimoto's conditional entropy is the best one, as far as I'm concerned. Okay. All right. Divergence is well known, so Rényi divergence. This time it's mu independent because it's defined in terms of this inner product. Okay, this is Rényi's definition. It's non-negative because of Hölder property that I talked about. So either Hölder or reverse Hölder, depending on whether alpha is less or greater than 1. And you recover Kullback-Leibler divergence, of course, when alpha tends to 1. But you also have some more interesting properties, like if one of the distributions is uniform, you get a relation between alpha divergence and alpha entropy, and which means that log of m is the max entropy in this case. You have the binary expression, and you have more. You have data processing. Data processing for alpha divergence means that if you process different distributions, so P and Q, well, at the output, you would decrease divergence, okay, with the same transformation. So same P of y knowing x. And this is easily found by looking at the golden formulas I told you about. There's a simple application of this. For example, if you have like a binary transformation, okay, that just gives you a 1 if x belongs to A and 0 otherwise. Then you get a lower bound on the alpha divergence as the alpha binary divergence, which has a very simple expression, okay, in terms of the probability of x belonging to A. Another example is a binary example where you have some quite trivial properties about alpha binary divergence, okay? You can check that easily. Next, we have another definition of kind of alpha divergence that has been proposed in the literature, and that's a definition by Sundaresan back in 2007, and it's now called relative alpha entropy. So there's a distinction between alpha divergence and alpha relative entropy. For alpha equals 1, of course, it's the same. Okay, and it turns out that in this case, I will not go into the details, but in this case, you can actually have an interesting variation of Gibbs inequality for any alpha. Okay. So next is mutual information. So what do we do with mutual information? So again, there is, according to me, only one good definition for alpha mutual information. There has been many definitions proposed in the literature. So the appropriate definition that I find useful is the following. You consider the alpha divergence between the conditional distribution, P of x knowing y. If you do y knowing x, then it will be different in this case. So x knowing y for a given y, okay? Divergence between this and px not knowing y. And then you have to average over y. And again, you do that inside the logarithm. And you obtain this definition of I alpha of x and y. Okay, so that would be expressed as such, using Fibonacci theorem. This was actually a proposition by Sibson back in 1969. Okay. And of course, it's mu independent because it's still defined in terms of the inner product. It has this uniform expansion that I really like. That is, if one of the random variables is uniform, then you have this relationship between alpha information and conditional alpha entropy, which does not hold in general, okay, this time, except for alpha equals 1. And it's not mutual as well. So you have to distinguish between I alpha of x and y and I alpha of y and x, okay? And it has many interesting properties, like this golden formula, which is known as Sibson's identity. So I don't know if you know that. Yeah.
The fact that it's not mutual seems to suggest that you can't define it in terms of the joint probability of x and y. Right?
Yeah, I feel mutual is more like information brought by x to y is the same as being brought by y to x. So it's not the same. It's not the case in here. Okay. Okay, that's what I feel, but I mean, you might have a different idea. Okay, so Simpson's identity is a very interesting equality identity that says essentially, well, you can decompose an alpha divergence with some qy, and it decomposes over some, your q star, there is some optimal distribution here, and plus I of alpha. So I of alpha turns out to be the minimum of alpha divergence over this QI. So, and in particular, it's non-negative, of course, and it's zero only in the case of independence. And data processing holds as well. You can actually use that property here, and then consider a general Markov chain, and whenever the random variables are farther apart, then the alpha information is less. Okay, It's just a simple consequence of the data processing inequality for alpha divergence in this case. So we have all the nice properties, and of course all the other definitions that have been proposed in the literature do not satisfy all these properties. So yeah. And just a word on. Oops, where am I? So this one, okay. Just a word on conditional alpha information. This was not in the paper. This is even more recent. We found what I feel is the best definition for conditional alpha information. So again, here we want to define the emitter information between x and y given z. So what you do is you fix the z, and then you have to average over z again, and you average inside the log. And this was never proposed before. And so we have this definition of I alpha of x, y, z, which turns out to satisfy all the important properties that we need for this quantity. And the other definition that had been proposed earlier did not satisfy all of these. Okay. Anyway, so going back to, okay, what is alpha information theory? So this parameter alpha gives you like more flexibility, okay, to manipulate the information between random variables with all of these nice properties that we proved. And in particular, when alpha tends to infinity, there's something interesting happens. Like for example, suppose that you have a Markov chain x, y, x hat. What does it mean? It means that x is like, for example, something that you want to know, okay? It's something that is unknown, but you want to know something about it. You want to know some information about it. And you have access to y. Y is an observation. And so you want to derive the x hat in such a way, so if x is a like discrete or memory variable, you just want to minimize the probability of error, okay? And you have the famous Fano inequality. So where am I? I thought it was. Yeah, it's skipped. Okay. So Fano inequality would be for later on. So we have this probability of success. Probability of error is just 1 minus probability of success. Okay. It's well known that if you want to maximize the probability of success, then you end up with a MAP rule, maximum a posteriori probability rule. Okay. And so what is it? Ça se fait tout seul. Hein?
D'accord. Ah oui, il est un peu textuel.
Okay. Okay. Anyway, so the resulting maximum success is given by this particular expression here, in terms of P of x knowing y. And this turns out to be related to the conditional infinite entropy That is Arimoto's definition of alpha entropy for alpha equals infinity. And of course, when you don't know anything and you do like a blind guess, then you get the best probability that you can have is simply exponential minus h infinity of x, Rényi entropy over the infinity. Okay, and you also have something interesting about I infinity of x and y, which has been proposed by Isan, Wagner, and Kamat back in 2020 for quantifying the information leakage in a side channel. I will not go into the details here. So Fano inequality, I just want to mention that. Classical Fano inequality is this. It's just a upper bound on the conditional entropy. This is a classical case, alpha equals 1. So upper bound on conditional entropy as a function of the probability of error. All right? This is really important to prove converse coding theorems and many things, okay, in information theory. And it turns out that when x is equal probable, this is just a lower bound on the mutual information. So you can rewrite it as a lower bound on mutual information. The lower bound is given by the binary divergence between probability of success and the probability of a blind guess, which is just 1 over m for equal probable x, okay? And so this was generalized for any discrete x, not necessarily quite probable, by Hahn and Verdi in 1994. And this is given by this expression here. So it's essentially the same, but here you have the maximum probability of success, and here you have the probability of success for a blind guess, okay? And so I just wanted to generalize this to alpha information theory, right? Okay, so X again is like for example a secret. P of y known X is a side channel. Y is disclosed to the attacker, so that's the observation, and we want to attack. So what do? I use the DPI. DPI is data processing inequality. Say I of alpha x y is greater than or equal to I alpha of x hat is going. This is crazy.
It's connected to the other.
Mm-hmm.
It's connected to your computer.
No, we cannot.
Okay, anyway, so you can have like a...
You want to do the next one?
No, that's fine. Okay, so I of x and x hat is given by this alpha divergence between the joint distribution and some product distribution. And then you can use again the data processing inequality for alpha divergence, which gives you this with some p prime s, which turns out to be upper bounded by ps, the blind guess. And then you can apply the binary data processing inequality again to obtain the final result. So, whoa, come on. This is crazy. Okay, so the main theorem here is this. Okay, Fano inequality generalized to alpha information. Okay, and gives you an implicit upper bound on the maximum probability of success for a given as a function of alpha information for a given alpha information. So let me give you, let me give you, if I can, let me give you an application to side channel analysis. So in this case, we have like a cryptographic device that implements AES 256. Okay. And there's some leakage, okay? So you put some probes on the secure chip somewhere, and you can measure signals and so on. And so you have some leakage model, which is generally taken as a Hamming weight leakage model for some reason. And then so you have some noisy measurement. And then you can evaluate, so the main theorem goes like this, there's a lower bound on the alpha conditional information here, by the main theorem applied to this Markov chain. X and Y, the both phase X and Y are the vectors of all the Xi and the Yi's. And so you can evaluate I alpha using some Monte Carlo simulation because you have that closed form expression, which is very nice to implement. And then gives you an upper bound on the probability of success that you can have for any possible attack. It's very interesting for the chip designers. They want to know, what can be done in terms of attacks. And it also gives you, at the same time, a lower bound on the minimum number of measurements, what they call traces, to achieve a given probability of success. Okay. And we can, and in this particular case, we have a definite model, a leakage model, so we can actually also compute the optimal attack, which is a maximum likelihood attack in this case. Okay. And so these are the results. First, we need, this is a success rate, so probability of success, for different values of the noise variance. So let's say the red curves are for sigma squared equals 10, okay, whatever, it's a Gaussian noise. So the triangles are the bounds given with alpha equals 1/2. So it's been said that 1/2 is the best choice, but in this case it wasn't. The dashed line is for alpha equals 1. And the squares is for alpha equals 2, and it turns out that this is very close to the maximum likelihood attack, so the best optimal attack that we can have in this case. So it seems that in our case, alpha equals 2 is best. Okay. And in terms of lower bound on the number of measurements, number of traces to achieve like 99%, 95% of success, it turns out again that, of course, the prediction with alpha equals 2 gives you something very close to the actual thing. Okay. And so we were very happy with that. And I'm finished with my talk, and I'm happy to take some questions.
Thank you. There is some question here.
Just, I don't have a question. It was a very nice talk.
Thank you.
I just have a remark, maybe for your future work, that some divergence has been very recently generalized by a paper of Basu, I think in IEEE transactions.
Okay. By who?
Basu. And co-workers. I can give you the reference. Sure. And because Michelle and myself even generalized those. So
generalized to what? To divergences?
To make it more flexible.
Even more flexible.
Use a new parameter.
Okay.
For the Sibson diagram. Maybe
okay.
More interesting.
Okay.
We can show you on our paper on the archive.
Very good.
So maybe there might be some future work to do.
Okay, great.
If it's of help for the people in COVID.
We have to,
thank you.
I will take the last questions.
I have a question about.
Can you come near the Zoom, because we cannot understand you on Zoom.
Can you shout?
Take off the mask.
Okay.
I can shout. Is that okay?
Yeah.
Yeah.
Yes. So on slide 11, you have a DPI inequality.
Yeah.
And I'm curious because there's a strengthening of that DPI inequality.
True. Of course.
Where you can use the conditional entropy in the reverse direction. You can use the conditional in the reverse direction to obtain like an extra term that strengthens.
Oh, you mean a factor term, like the strong data processing inequalities?
I don't know if that's the name, but it has like a plus the entropy of some additional probability distribution you have.
Plus.
Yes.
Okay, so there's something called strong data processing inequality, in which you have an additional factor. This is a lot more advanced.
A multiplicative factor?
Yeah, it's called strong data processing inequalities. But so what do you mean is the difference between those two terms?
Yeah, like the relative entropy of, let's say, if you have
yeah, you can decompose.
EX, and then you push.
So for alpha equals 1, you can decompose. Not for alpha.
So it does not hold.
Yeah, because the golden formula that I told you about. If you go back to this, the golden formula. Where is it? Here, the golden formula. You see this is stuck inside the inner product. You cannot just move it outside. And taking the log, you don't have the plus.
I see.
So it's more complicated than that.
I see. Okay. Thank you.